Hello, welcome. We are waiting now for people to join in. We will start as soon as there is enough quorum at this particular IET webinar. We'll wait for some more time. Well, I think that with some more seconds, then we have sufficient people joining in. Yes, I think we can start. Welcome to everyone. My name is Gianni Cesel, and I am an IET member and volunteer of the Spanish local network. You are here joining at the webinar. This is a webinar about the Burst Observer and Optical Transit Exploring System, otherwise called BOOTES. This is a Latin pronunciation because the name came from a person from South Europe. We go to the next slide where I prepared a little bit the presentation of the agenda. Here you have a little bit an outline of the webinar. We are going to go through a short introduction where I will talk a little bit about the IET. I will introduce the speaker and I will make an opening to the main topic. Then we will cover the main topic with our speaker. This is going to be about the robotic telescopes or BOOTES. And finally, we will have also the opportunity to answer question and answer. You will be able to post your questions during the presentation, but you have to post them in the Q&A Zoom channel, not the chat, but the Q&A Zoom channel. Okay? Then there is going to be some closure. Therefore, just without further delay, what I'd like to do is go to the introduction and talk a little bit about the IET. The IET is one of the world's leading professional societies, and it caters for the engineering and technology community, and it provides a global knowledge network. In Spain, we are about 170 members, and we belong to the worldwide IET network. The IET Spain local network organized this webinar with the spirit of the institution to inform, inspire, and influence our community. We go now to talk a little bit about our speaker. Our speaker, Professor Alberto Castro Tirado, he obtained his PhD from University of Copenhagen in 1994. He gained his postdoctoral at Space Astrophysics and Fundamental Physics Laboratory. This is under the auspices Aerospatial Research National Institute. He was founder and head of the Robotic Astronomy and High Energy Astrophysics Group. He is head of the Stellar Physics Department, and he is responsible of the CISC Associated Department of System Engineering and Autonomics at the University of Malaga. He is also principal investigator of BOOTES, worldwide network of optical near-infrared robotic telescopes, and Cassandra all-sky cameras. We go now quickly to the next part, which is an opening to BOOTES, the Burst Observer and Optical Transit Exploring System. This was first designed as an set of autonomous telescopes and started to be deployed in 1998. It is a global network of robotic telescopes, being the first one presented in all continents as of 2022. We will review the several subsystems that account for BOOTES network and review its achievements over the last 2 decades. Moreover, we will hear about the advent of neutrino and gravitational wave detectors, and we'll discuss the role of the network within the framework of multi-wavelength astrophysics. Given this, what I'd like to do now is to call for our professor and speaker, Professor Alberto Castro Tirado. And for this, what I will do is switch off my screen and ask Professor Castro to switch on his screen. Professor Castro Tirado, can you switch your screen? Fantastic. Please go ahead.
Yes, good afternoon, everyone. I hope everybody could hear me. First of all, I want to say that it's a really big pleasure to give this webinar to all of you. And I appreciate the invitation by Joanne and Gianni to be here. And this is a very exciting project, which I conceived when I was doing my PhD thesis in Denmark, nearly 30 years ago. So I can say now that dreams come true if you work hard and go beyond them. So this project, it's a really wonderful project that I could have achieved because there are a lot of people working together with me, as you can imagine. So this is just a list of persons who are together with me, and I will just show them, just because first I want to highlight how the webinar will focus. I will start describing the network, what is the philosophy beyond the network, the science we can get, and what we can do now in this multi-messenger astronomy area that started a few years ago with the discovery of gravitational waves. Then I will end with the conclusions. So as I said, there are a lot of people working with me over the years in this project. The people who are still on board are listed here, but there are many other people who work at some point in the project. And these people are from many countries because, as Gianni said, the network is already deployed in the 5 continents. So I will just not quote the names, but I will show the institutions, partner institutions, which are there. The upper ones are the ones here in Spain. My home institution, which is the Institute of Astrophysics of Andalusia, which belongs to the Spanish Research Council. And then it's the National Institute for Aerospace Technique, INTA, the University of Malaga, and the University of Huelva. And then here you see the logos of all the other institutions in the other continents. So I will just start showing that 25 years ago, I managed to put a small telescope, the blue one you see on the upper left corner, in a wonderful place here in southern Spain, in Huelva. Huelva is close to Portugal. It's where we have the largest European national park, Doñana. I think you have heard about that. So on the bottom left picture, you can see the trees of pines, trees behind, so we can have access to the entire horizon. And this is very important for the science we wanted to do from there when we deploy different instruments in the following years, 2000, 2006, 2009, 2016, and together with other Spanish institutions or together with other institutions abroad. An example of a collaboration with a Spanish institution is the Spanish Patron Meteor Network, together with the University of Huelva, in which we install video cameras pointing to different parts of the sky in order to record meteors. And together with the University of Warsaw in Poland, the picture on the bottom right was an asset of 4 equatorial mounts that each of the mount had another 4 lenses, wide field lenses, in order to cover pi stereo radiance in the sky. That's the reason of the name Pi of the Sky. This was also a very successful collaboration. And in the last years, we installed a wonderful instrument, which is here in these 2 pictures, together with the 2 engineers I have in the team, Emilio on the left, Ignacio on the right. And this is a wonderful instrument because it can provide, depending on the camera you have attached, a 3x3 degree field of view or even a 5x5 degree field of view. And we use it to monitor the sky on a nightly basis. This was the first station we installed in 1998, with instrumentations that has been evolving over the years until the telescope you see here. But already 3 years after the installation of the first station, we decided to move to a second station, not to move, to build a second station, which we managed to do in the Malaga province, also in South Spain. And the reason is just because the number of sunshines and namely clear nights we have in southern Spain is really huge, as you know. That's the reason why we have so many tourists in southern Spain. And we decided to start installing a similar telescope as the one we have in the first station. But in 2008, we decided to go for a larger diameter telescope. So instead of a 30 centimeter diameter telescope, we put a 60 centimeter diameter telescope. The image you see on the right side is the conceptual design of the telescope, and the real telescope you can see here. So this is telescope. It's called Telma, Telescope Malaga, because Malaga is the province where the telescope is sitting, and you see the dome, which is hosting the telescope. In 2008, we could image stars as fainter as 20 magnitude. Just for those of you who are not acquainted with the system of star magnitude, the faintest stars you can see by naked eye on the sky in a dark night when with no moon is about 6 magnitude. And with this telescope, we can reach 20 magnitude, and each magnitude unit different is a factor of 2.5 in brightness. So we are starting gathering images of stars and galaxies and planets and so on. In 2008, in 2011, 3 years after, we developed ourselves an instrument that could get a spectra of the targets. And this is the so-called colorless instrument, which could pinpoint stars as faint as 16 stars, galaxy, whatever, at 16 magnitude, and get a spectrum of these targets. This is a detailed view of the instrument with the optical system on the bottom image, and with the real instrument. When you remove the cover you saw on the previous picture, the cover where colorless name is written, when you remove this cover, then you see the content, you see the camera, H label, and then you see the filter wheels, C and A, where we also have the grism in order to decompose the light of the stars. The field of view is about 10 by 10, and then we have resolution, which is low, but resolution for getting information of these targets. In year 2009, so it was 11 years after we deployed the first station, we decided to move to another country. And then we decided to move to New Zealand, because New Zealand is just opposite to Spain. So in order to maximize the coverage at the other time of the day or night, we went there. And you see the image, which is really wonderful, because there is very little light pollution there. You can clearly see the Milky Way on the zenith right above you. And the picture you see on the upper right side is just the image we get with the all sky camera device, because we have an all sky camera in each of the enclosures hosting the telescope. So with this all sky camera, we are also getting images of the sky every 1 minute. And this is important for two reasons: for science, but also for controlling the cloud cover, because we are dealing with a robotic system. So it's supposed that the system have to take care of the weather conditions in order to continue observation, or to stop observation and closing the dome or opening the dome. So as I said, we went there in 2009 to the South Island. First, we went to the north of the South Island, and then in 2014, we decided to move to another location, much closer to the southern border of the South Island in New Zealand. This was 2009 when we opened the station BOOTES 3 in New Zealand, and in 2012 we moved to China in order to install there the fourth station of the network at the Lijiang Astronomical Observatory, 3,000 meters high. This is a picture of the site, and the one in the lower left is when we opened the station with the Chinese and Spanish authorities there. The telescope in New Zealand, telescope in China, and the rest of telescope are all 60 centimeter diameter, which are just a clone of the telescope we have in Malaga, in station number 2. In 2015, we also decided to complete the network in the Northern Hemisphere. So we deployed the 5th telescope in Mexico, in San Pedro Martir Observatory in Baja California. And this is close to the Pacific Ocean, and just also very close to the US border at a height of 2,300 meters. When this installation was completed, Spain was the first country to deploy a network of telescopes in the Northern Hemisphere. So we still were missing the stations in the South Hemisphere other than New Zealand. And in 2021, we deployed the station in South Africa. It was quite challenging because we had a pandemic affecting all of us. It was really challenging to manage and deploy with the pandemic going on. This is just a picture when we opened the station, and with people from the University of Free State, which were very helpful to us. And finally, in December last year, 2022, we deployed the last station we were missing in Chile, in San Pedro de Atacama Observatory, 2,000 meters high, again, one of the driest places in the world. And with this installation at the Space Observatory, Spain was the first country, together with the other countries which were helping us over the years, to lead and deploy the network of telescopes in the 5 continents and completing a worldwide network. I was very happy when we could complete this puzzle, this picture, showing the small insert of each station, because, as I said, it took 25 years of my life to accomplish this work, and with a not very high budget, with a small team, but very enthusiastic person, managed to get this done, and combining the efforts of scientists and engineers working together very hard over the years. So, what is the philosophy of the network? Why it's important and network of robotic telescopes around the world? Well, I would say mainly because of 3 reasons. First, the first one is that if you could go from the North Pole above the Earth and look downwards, you will see that the 3 BOOTES stations in the Northern Hemisphere, BOOTES 1, BOOTES 5, and BOOTES 4, they are equidistant each other. So basically, it's nearly 7-8 hours difference between each of them. And when you go to the south, if you could just go above the South Pole and point downwards, you will see BOOTES 6, BOOTES 7, and BOOTES 3. So basically, this is telling us that eventually we could follow up any event in the sky, any event in the sky, if the weather is okay, because when in one station the night is ending, in the following station the night is starting, and so on. So eventually you can track the night side of the Earth from each station and point to your favorite object in the sky. So this is important. And on the other side, it's very important that each of the 6 stations containing the 60 centimeter telescope, they have, as you see below in this slide, have identical filter system and identical cameras, CCD cameras, to record the light of the faint objects. This is very important because then you can combine your data without any issues of different colors systems or different quantum efficiency of the camera recording the light, because the cameras are identical, the filters are identical. So this is an advantage when you want to combine data from different observatories from one place to another place. So this is one very important issue. And another important issue is that we can support from the ground the spaceborne experiments, which are providing wonderful science data. We can do this thanks to 3 other characteristics. The first one is that each of the telescopes, they have very fast slewing speed, so they can move from one side to the sky to the other side of the sky in about 10 seconds maximum, because the slewing speed is just amazing, 100 degrees per second, and the acceleration is 10 degrees per square second. That is one very important property of the system. Then software. We have a software which allows easy rescheduling of the objects we are observing. And this is also fundamental because then you can respond to alerts going out on the sky. And the third property is that the camera can take images with a very fast readout, less than 1 second. So you can get many images in short time scale because the readout time is negligible. So just an example of 3 spacecraft, scientific spacecraft we have been helping from the ground, but there are many of them. It's just the Integral Gamma Ray Laboratory, which was launched by the European Space Agency in 2002, which is still in operation. The Neil Degrassi Swift spacecraft launched by NASA in 2004, is still in operation. And then different experiments at the International Space Station, such as the MAXI module or the AXIN experiment, which is also on the International Space Station. But this is just a few samples of the science spacecraft we are helping from the ground. Now let me go to the science we can do with the network. The main goal of the BOOTES network, the name, by the way, is just because we wanted to mimic a constellation in the sky, which is called BOOTES, and then we found an acronym for the name of the constellation, which makes nice what we were doing, Burst Observer Optical Transient Exploring System. The main scientific goal which I had on my head when I conceived the experiment was gamma reverse. 30 years ago, gamma reverse were one of the biggest mysteries in astronomy. They were discovered in 1967, and we had no idea of what was going on with these events. We knew that they were the most energetic events in the universe, but we didn't know the distance scale. So definitely we had to help the high energy detectors on board spacecraft from the ground to identify the optical emission in order to shed more light on what was the nature behind. So when I had this project in mind, this was the main goal. Gamma reverse, as I said, they are the biggest bands in the universe. What you see on the left image is just how gamma reverse look like. So in a few seconds, from a very low background we have coming from all the universe, we have a point source that at the peak of the mission outshines, as you see on this image, when everything it gets white, outshines the rest of gamma ray sources in the universe. On this image, the red horizontal bar is the galaxy, our galaxy, Milky Way, shining in gamma rays. Blue parts is what we see above and below our galaxies, and the point which is shining there and becoming white at a given point when it reaches the maximum is when the burst outshines the rest of the universe. It took many years, 1998, to discover that these events happen in distant galaxies. And this is one image of the light, optical light, of one of these gamma ray bursts superimposed to two interacting galaxies. So these objects, this explosion, happened very, very far away from the universe. And we can say now that they are the most energetic events which we can see in the universe, with the exception of the Big Bang, which originated our universe. So what happens when a gamma ray burst goes on? And this happens about once a day. So the source producing these gamma ray events for a few seconds happens to be detected by many spacecraft on board, instruments on board spacecraft around the Earth. And they can determine the position very quickly. And when the position in about 20-30 seconds is determined, this can be transmitted to the reception antenna ground, and from there through a system which is called GCN, which is called the Gamma Ray Coordinate Network or Transient Alert Network, we get the position sent by internet to optical telescopes, to radio telescopes, to the electron volt site where we have gamma ray observations at very high energies, or even to our mobile phones. So we get an alert every now and then of a source which is outbursting in the sky. And so that's our network. Each of our telescope gets these alerts, and they can point quickly to this position of the sky. What is going really there? We have a central engine, which is producing ultra-relativistic jet, and we have different shells of matters which are being expelled from the inner engine at relativistic speeds, and these shells are interacting each other because they have different velocities. So first they start producing a given number of internal shocks, which are the gamma rays we see, and the external shock encounters the interstellar medium of the galaxy where the source is laying, and this produces a forward shock and a reverse shock at the same time. And the forward shock makes cooling of the electrons that are in there, and then what we see is cooling down of electrons, producing at the end a synchrotron spectrum, which is evolving in time, and with the peak of the emission of the synchrotron moving from gamma rays to X-ray, ultraviolet, optical, infrared, and radio as time goes on. I think you can see this clear on a later image I will show, but this is just a real example of two of these gamma ray bursts, two peaks of the same gamma ray burst, which was observed on year 2016, the 25th of June. And you see at time zero, this is tiny peak, which is what we call precursor, and then there is nothing until nearly more than 3 minutes when we see the big emission with different peaks and so on. The black curve is the gamma ray emission, and the colorful points are the data we got in our BOOTES 1 station. So what you see in this image, or in the right image where we see a blow up on the other image, is that the optical emission does not really track the gamma ray emission. It's different. So clearly this is telling us that there were two main components at this time. This is what I can say, just an example regarding these simultaneous images we can get when the telescopes are pointed within 1 minute to the burst itself. But what we do most of cases is to follow the afterglow emission, which I mentioned before. When these gamma rays encounter the interstellar medium of the galaxies, within minutes, what we see is the emission at other wavelengths than gamma rays, optical, X-rays, ultraviolet. What we see is just how the synchrotron spectrum on the lower right bottom image, the synchrotron spectrum evolving with time, and the synchrotron peak moving from X-rays to optical to infrared and ending in radio. This is the same on the lower left. This is the same, but with different colors. And the stars showing up here in the right bottom upper image, sorry, is the real image of the gamma ray afterglow light in the optical, outshining completely the galaxy where it was produced. But we can also do other science, which is targets much closer than us. In fact, the system we have is quite powerful to image meteor, including fireballs. Fireballs are the meteors which are really bright, and these are the ones that we may see even if we are in the center of the towns, because they really could be as bright as the full moon in some cases. And what you see on this animation is a series of images with a 1 minute iteration. And once the meteor, what you see right now, is gone, we still can see the trail, which is being distorted due to tropospheric winds. But sometimes the fireballs are so bright that we can try to determine the infall area of the meteorites that may have produced the parent meteor. So this is an image, a part of the image, about a quarter of the whole sky image that we get every minute with one of our cameras. For those of you who are familiar with the sky, this is the Orion constellation, right? Orion constellation. This is the horizon, and the full image was just about 4 times this one, right? Covering the whole sky. So this is an image taken 1 minute before a very bright fireball was seen. And the next image is the one you can see now. This image, you see the full entire horizon is just outshined by a fireball. This fireball we see in the horizon because it crossed the sky more than 400 kilometers from us. And this camera is based in South Spain, and the fireball happened atop the Morocco border with the Mediterranean Sea. And we managed to determine, because this was detected by 2 cameras, we managed to record the infall area of meteorites, and it happened just 100, 200 meters away from the coast in Morocco. So we didn't expect that the meteorites could be recovered unless somebody could go to the bottom of the sea. I think it was rather than 200 meters, or something like 1 kilometer or so. Anyhow, this showed and proved the powerfulness of these devices for recording anything moving on the sky, right? So this is just some example of what we can do, the science we can do in our solar system, but it's not the only one. As you know, Pluto is the most representative dwarf planet. This is an example of what we did with Pluto in 2015. We knew that Pluto, which is the object which is I'm pointing with the mouse, was getting close to a star which is farther away on our galaxy, on 29 June. And within 3 hours from this image, it was going to pass just in front of the star, of the background star. And we were so lucky that our BOOTES 3 station in New Zealand was going to be right in the path of this phenomenon. So we observed the star's brightness before it was going to be occulted by Pluto, and then during the occultation. So this is our record of the brightness of the star, the so-called light curve. And this is the brightness of the star when before occultation, after occultation, and when Pluto was occulting the star, the light of the star decreased very quickly. And then we see this flash right at the middle of the occultation, and then the star recovered the light afterwards. The fact that the light decreased gradually and not suddenly confirmed that Pluto had an atmosphere, as we knew beforehand. But we could model this, and also the flash, which was expected from the theoretical point of view, and could determine some properties of the Pluto atmosphere that were confirmed just a few weeks after, when the Pluto flyby passed away from Pluto, launched by NASA together with European Space Agency. So this was a very wonderful capability that we could show at that time. We could also observe other objects in our solar system, such as comets. This is an image on the right of one of the brightest comets we have seen this year, the comet 2022 E3. And we also managed to get a spectrum of this comet with this instrument I showed you before, the Colores spectra. And I can tell you that it was not easy because the comet is moving. So you have to track the comet with the speed that the comet has in order to get this wonderful result. We can also search for extrasolar planets. You know that there are more than 5,000 extrasolar planets discovered so far. How can our network contribute to the discovery of extrasolar planets? This is just an example. This is by means of the microlensing technique. Here on the left image, you see the Earth, and then you see a distant star. And we may have another star in between. And this star in between may have planets orbiting around it. So if the Earth and the stars with planets around and a background star are perfectly aligned, and this may happen because this star in between is just moving very slowly in front of us and of the background star, the light of this star in between, the light of the star at the background will get amplified by the star in between. So we will see that the light of the star, and this is, you see this on the right image, the light of the background star will start being bright, increasing until reaching a peak. If the star which produced the amplification has no planets around it, you will see just a single peak. But if the star does have planets, you will see these secondary peaks, which you can model and then determine the mass of the planets and the distance to the star of the planets. And this is the way how Jovian mass planets were discovered in many cases using this microlensing technique, and we are contributing to this research as well. Now I will focus on other objects in our galaxy that are very interesting and from which we can learn a lot. These are so-called flaring stars, which are active stars in which there are magnetic fields going on the surface, and sometimes we have a process of magnetic recognition. And there was one particular source, which is called DGCVN, which happened to have two outbursts within hours only separation. And for the first outburst, we got the alert, and we point, or our robotic telescope point by themselves, as they do. We catch the tail of the burst, but after 2 hours, we were so lucky that a second burst happened. And we were so lucky because we were already getting a spectroscopy of this star, of this flare star. And we saw how the system during the flare evolved and became very, very blue for a few minutes, and then it decreased again and returned to the quiescent state. So we were very lucky to see this spectral evolution, which we managed to publish and to model and to propose an explanation, also showing the powerfulness of the system. And recently, we have also tried to shed some light on a source which houses the highest magnetic fields in the universe. These are so-called magnetars. Magnetars is a neutron star in which magnetic fields could be as large as 10 to the 15 Gauss. And this is just, I mean, amazingly, you cannot imagine how huge is it when you compare with the magnets which we all have on the refrigerators, which are much less than 1. So we try to image the optical emission of magnetars at the time of a bright outburst. We get no optical emission simultaneous to the flares in gamma rays, but it was important also to constrain the models. And I think we did pretty well in a couple of cases here. The system, especially the units, the telescopes with the wide field we have in the station number 1, but also with the help of the all sky cameras we have in all other stations, are quite powerful in order to detect transient sources. You should know that we are doing sky surveys on a nightly basis down to 15th magnitude. And any new source or variable source, we can image it, and we can report if there is a extraordinary outburst. And we are doing so, and this is just an example of 3 of these sources you see here, which we could detect. For example, the new star Nova Cassiopeia in 2021, a prediscovery image before compared to the catalog. Then this was another star which is belonging to the cataclysmic variable system, from which we managed to get it in outbursts and get a spectrum out of it, or the monitoring of another systems in our galaxy, such as this particular source SW-UMA, that was obtained by the system itself, and the data reduced and the light curve shown there. But probably what is more on fashion right now is the possibility of getting science in the field of multi-messenger astronomy, mainly gravitational waves and neutrinos. As you know, gravitational waves was a new field which was open to the science in year 2015, when the first gravitational wave were discovered on the 14th of September 2015. I like very much this image you see here, because this is the first image simultaneously to a gravitational wave ever detected in the history. We had our all sky camera getting images in New Zealand on this day when the first gravitational wave we detected arrived to Earth. And this is the first image, and these curves here, they represent the uncertainty region of the gravitational wave. We did not record optical emission, unfortunately, but at least we could set some limits on the optical emission. And this was, I think, from the historical point of view, an important image. Then we were much luckier in year 2017, when another gravitational wave was detected on the 17th of August. And so far, this is the only gravitational wave for which an electromagnetic counterpart at other wavelengths were detected. This is on the lower left image. You see here a uncertainty region determined by the gravitational wave detectors and by the Fermi gamma reverse monitor, which detected a faint gamma reverse simultaneously to the gravitational wave. And within this uncertainty region, many robotic telescopes and human-controlled telescope on Earth managed to detect a counterpart. This was this object here, which you see in less than 1 day after the gravitational wave was recorded, and nothing was seen 2 weeks after. This object underneath is a galaxy, galaxy NGC 4993, at a distance of only 40 megaparsecs. This was the counterpart, optical counterpart, and the gravitational wave. As I said, this was the only electromagnetic counterpart seen to a gravitational wave so far. This is an image obtained by a telescope in the southern hemisphere, and we were very proud to have the only telescope in the northern hemisphere which detected the object. The gravitational wave is here, and this is the galaxy. And we managed to detect the object because our telescope in Mexico is designed to point towards the horizon. So we can point just 0 degrees above horizon, and this is very important for us to detect this emission. So together with other telescopes in the southern sky, including the very large telescope in Chile, we could follow up this event to get the spectroscopy as time went on, and to confirm that what we call a kilonova was underneath, and this kilonova was associated to the gravitational wave. And what we could model is that up to a 0.05 solar masses were ejected at the speed of 0.2% of the speed of the light, and that this spectra was evolving, and we could for the first time confirm that a gravitational wave was related to a short duration gamma reverse, and it was related to the merger of 2 neutron stars. Gamma reverse can be produced by mergers of 2 neutron stars or by the collapse of very massive stars. And in this case, we could nicely confirm that the mergers of 2 stars produce kilonova and produce gamma reverse and produce gravitational wave. Wonderful events that allowed to reply many questions, although many other were open afterwards. So what do we do? How can what we do with the BOOTES networks when we try to follow gravitational waves searching for optical counterparts? In the case of black hole mergers, which are one of the objects that are producing gravitational waves, the problem is that we have an uncertainty region over the entire celestial sphere, and sometimes it's really challenging because you have to tile and get some mosaic in order to cover the whole region, but then you cannot go deep. So probably if there is a counterpart, which is basically very low probability that we have it in case of black hole merger, it's going to be very faint, and I think so far we are getting null results. In the case of neutron star mergers, like the one I showed you in 2017, I think we have a better expectations. This happens about once per week, and sometimes what we have to do in the error boxes where the object may be located, we have to monitor the galaxies in there. The gravitational waves detector can tell us the distance, the range of distance where these gravitational waves are produced, and and we can pinpoint and select beforehand the galaxies in this part of the sky at this distance range and try to monitor each of them in order to find a new star-like object in the outskirts of them. We made use of a catalog of galaxies, which is called the GLADES catalog, but sometimes the number of galaxies in these regions can be 1,000 or more, and a single telescope can hardly image more than a few hundred galaxies at a given depth. So if the number of galaxies to image is larger than that, then you need an asset of telescopes to do the work together. So we have already some expertise regarding the follow-up of these gravitational wave events when we look at the so-called observing run 3 that happened for 1 year since March 2019 until April 2020, when due to the pandemic, the gravitational wave detector had to stop. So during this a little more than 1 year, there were 72 triggers, gravitational wave triggers. Many of them were 35 black hole mergers, where we know that optical emission is really to be challenging. But 16 of them were neutron star mergers. These are very interesting because we expect optical emission out of them. We were able, with the different BOOTES telescopes around the Earth, we were able to follow 55 events, 30 of them neutron star mergers. And unfortunately, none of them shown any optical counterpart, as all of the people who are researching, unfortunately, happen to know. This is just one example. The one of 25th April 2019, it was the first binary neutron star event reported, and we knew that the distance range was 156 plus minus 41 megaparsecs. It was very likely to have a neutron star merger there, so we tried to observe each of the galaxies underneath there, and this is just an example. We tried to image many galaxies, all of them as seen here. Fortunately, no new star-like objects close to these galaxies were present down to 20 magnitude. So neither us nor other teams in the world managed to find counterpart here. So now we have a big expectation in the so-called O4 run. The O4 run, 18 months run, started in May this year. So it's already 4 months since the start of O4. And so far, no other promising event such as the one I showed you in August 17 was discovered, but we still have more than 1 year in front of us, and we expect that sooner or later, in the months to come, we will get another close binary neutron star merger, and we expect that with our network and with other teams in the world collaborating each other as we did in the past, we could get an extramagnetic counterpart to continue shedding light into these gravitational wave emitters. I want also to mention about neutrino sources as the other side of this multi-messenger astronomy. We have followed up half dozen IceCube alerts already. Neutrinos are also quite elusive sources. No counterparts have been pinpointed so far, with the only exception of a blazar, which was related to a 2017 event. And this is also a field of research in which we want to try to contribute. And we are also trying to tile and get observations of these uncertainty regions, which you need many square degrees to image. And also you need a software to try to determine if you have a transient there or not. So let me just go to the conclusions. Now I can tell that the BOOTES network is complete. Proudly, I can say that after the last 2 stations were deployed in South Hemisphere, South Africa and Chile. There is a lot of technological development here because one of the things we want to do is to coordinate the observatories to make a single telescope system, perhaps a future intelligence system, and that the gamma reverse are the most energetic phenomenon in the universe, and this is one of the main targets of the network. Just to tell you that the number of peer review papers, including BOOTES data, are more than 70, including several in Nature or even Nature Astronomy, the one I published this month in the control mission section, detailing the network, and then sky surveys and the search for extrasolar planets, gravitational waves, and so on are also additional scientific goals. I think we have, especially in the light of the O4 run for gravitational waves, we have a unique opportunity to help in this exciting scientific field. Let me just end announcing that in 2.5 weeks from now, we will have again, as every 2 years, the workshop on robotic autonomous observatories here in Spain, in Malaga. We nearly 100 scientists and engineers will gather, and this will discuss how to move on, how to use artificial intelligence to analyze the data, to discover transient and so on, but also will focus in educational aspects, which I think are important to foster STEAM in the younger generations. You have the web with the information about the conference, and then you have the Twitter or the X, we say now, for the conference, and mine down there. And I just want to thank again the chance to give you this webinar. Thank you again to all of you.
Thank you, Professor Alberto Castro Tirado. What I would like to do now is to share the question and answer questions that we received. So let me put on the presentation, because in this way we have this time. Okay. And we'll go for the questions. So I'm going to read out the first one. And one of them will say, why did you move your telescopes in New Zealand further south? Why didn't you move your telescope in New Zealand further south to the current position?
Yes, this is a good question. And the reason is just because for the first 5 years, the telescope was located in the backyard of an amateur astronomer, an engineer, Bill Allen. Bill Allen was already retired, and he offered us the chance to deploy the telescope in his backyard, because he also have his own amateur astronomy telescope there, and he offered us that possibility of he will take care of any need that we may have in case of rebooting a computer, if there was some failure, whatever. After 5 years, he felt he was too old to continue doing this job, and then we decided to move the BOOTES 3 station to an official site, as we have done in all the other installations around the world. So then we moved to the research area owned by the National Institute for Water and Atmosphere in New Zealand, NIWA institution, and there we have the BOOTES 3 station now, and we found that it's better that you have your installation on an official site, even if permissions will take longer and so on. But this was the reason. This was the reason for that. And I really thank Bill Allen that he helped to host the telescope. And in fact, the telescope in New Zealand was dubbed, and still is, Jock Allen telescope, because Phil Jock was an astronomer in New Zealand University of Auckland who helped us a lot, and Bill Allen who offered to have the telescope on his side. So that's the reason why telescope is called Jock Allen telescope in B3 station.
Excellent. Thank you for the answer. It was quite exhaustive. So I'd like to ask another question, and this is with all the engineering work that went into making up these devices and telescopes. Were there any patents or any breakthrough in the technological terms?
Yes, that's a good question. Because as I said, we have a synergy between scientists and engineers here. And we developed several things already specifically for our project, which now nowadays can be used by other teams. The first patent was this all-sky camera, which we are using to image the sky every minute. At that time, 2005, the conception of the device and the software associated was completely new. So we decided to patent this system, and it's being used in other observatories, especially in Spain. But this was the first one. The second one was the enclosure, the automatic enclosure, 2 halves, opening and closing, with a Zelio controller, and taking into account the values, the input values from a weather station, namely the precipitation value, the wind, the humidity, and so on. But specifically the precipitation, we have a precipitation sensor. So this system of control and the opening, close, and open was also a patent. And they also have the spectrograph. I showed the color spectrograph, image spectrograph, was also patent because it was a new concept for imaging spectrography. And then we have also an utility model, which is the time stamp we put in the images. One of the things we are doing with the network, which I had no time to comment on, was that we are doing a space surveillance. So we devote a fraction of the observing time to monitor space debris, which, you know, this is going to be a really huge problem, because there are many satellites which are populating the low Earth orbit and also the geostationary orbit. So there is a lot of increasing interest to monitor these satellites to prevent collisions in the future. So especially at low orbit, you have to get very fast images with 1 second time iteration, and then what you see is a track in the image of the part of a space debris. So you have to assign a time, very precise time, to determine the orbit and to pinpoint the trajectory. And you need very precise time stamp when you get an image of 1 second or even less than 1 second. And you have to get a time stamp with a precision of less than 0.01 second. So we had to create a system in order to get the timing from a clock, and to put this timing on the image as soon as the image was taken. This was also important for us, and this is also something that is being used in other devices now.
Fantastic. It was quite interesting to hear. What I would do now is to ask one last question, because I think that we are close to the hour. Well, a little bit past, but I think we can go for one more and then we close. Across the whole network, how many days of cloud cover do you have per year? Would you like to add more sites if possible?
Yes, very good questions. Very good question. Yes, we are open to add new sites, but if we add a new site, the telescope and the camera and the filter should be exactly the same. This is what we request. And about the fraction of a clear night, depends, but they range between, I would say, 80% in Chile. This is the maximum, about 80% in Chile, to 50% in New Zealand. In Spain, it's about 70%, also in South Africa. In China, it's about that, taking into account that monsoon period in China between June and September prevents you any observation. So, for example, another location in Asia will be interesting. In New Zealand, if we could get a telescope in the Northern Island, would be very interesting also, because there is some sort of anti-correlation in the climate between the Northern and the South Island. So if we get a second telescope in the Northern Island in New Zealand, the 50% percentage of clear night we have now with only one station, I think it will increase to 65 or even 70% if we have a second station in the Northern Island, just to give an example. But
Excellent. That was a very insightful presentation. Unfortunately, now we are very well past the hour, and we have to close. So I would like to thank everyone who joined the webinar. Special thanks to you, Alberto, for joining us, for sharing your knowledge with us.
pleasure.
Thanks to everyone, and also to the staff of the IT who actually helped to set up and operate the streaming instrumentation and the application. And what I would like to wish is a very good day to everyone. And hopefully we will see you again in one of the IT webinar. Have a good day and goodbye. Bye-bye.
Bye-bye.